Okay, so without further ado, by the way, love the title from Road to Code. I believe this is a very important topic in general. I've been saying for a while. I don't understand why it's not done in a neurosymbolic way. Self-driving cars more deeply than I know of. So I think, of course, it's many people feel neurosymbolic AI is the way to get things safe. There's no better poster child of the need for that than this area. Okay, so here's a bit about Sridhar. You can find out more on his site, and he listed the paper here he's going to cover, and we're going to put this on the Discord's discussion so that you'll be able to find out more. Okay, as usual, multiple places you can ask questions and I'll follow the talk. Okay, all of them will feed into Olga, who's going to relay them to the speaker. Okay, and without further ado, let me hand it over to Sridhar.
Okay. Yeah. Thank you. Great. So yeah, if if anyone has any clarification questions, I'm happy to pause in a bit. I just say something and I'll pause and clarify something. So this is the title is From Road to Code. The basic idea is to use some neurosymbolic techniques for synthesis and analysis of autonomous vehicle scenarios. Although I'm the face of this work, figuratively, this has been made possible only with a lot of collaborators. I will talk about the paper that Alex shared, but I will also talk about something more that has been going on. Look out for this space. We have some exciting new developments and some new results, which I will give a hint of in this talk. Okay, so what is this about? Maybe if I can capture it in one slide, this is what it is. So, if you think of autonomous vehicles as an important endeavor for humans in general, I think a lot of people are frustrated with spending so much time driving. So, autonomous vehicles will hopefully be here soon and save us from this drudgery. Um, if you want to have them work in a reliable, consistent, in a diverse number of scenarios, we need some way to evaluate them, not just evaluate them, but evaluate them in a very rigorous manner. So, what this does is it is a way to capture a real scenario and then transport the scenario into a virtual world of your choice that you have built using your favorite tools. And how to do it is what we plan to show. Again, the this is still a work in progress. So here we have a particular figure where on the left side we have the vehicles that are actual road with a few vehicles, and on the right side you have the same or similar scenario completely transported into a simulation environment. So okay, where is or what's the need for doing this road to code, right? One of the big applications of this, the way I see it, is in autonomous systems. So autonomous systems have been one of the major drivers behind many enhancements in machine learning technology, like for example a lot of image recognition, object detection. All of these have been classically machine learning problems, but they got supercharged by a big application of driving autonomous vehicles safely in crowded environments. Again, if you are driving in isolated environments like space or say F-16s, then autonomous systems do not need so much of machine learning components. But again, one of the fundamental problems in making these autonomous systems reliable is to make sure that they work properly. And how do we make sure that they work properly? Well, other than formal verification, which is what my bread and butter is, one of the ways where we can give at least a lot of confidence in these systems is by testing. Again, even when we do formal verification, a bit of testing is important, because there is a famous quotation by a Turing Award winner saying, "Oh, I've just proved the system right. I haven't tested it yet." So, what does it mean? There are a lot of abstractions that we need to make when we do any sort of formal verification or formal analysis. The real world system often deviates from the ideal design in many ways. So, testing is still indispensable. Just to put it in, most of the autonomous vehicle companies now, they do beta testing over specific roads, and they picked a certain venues, and there is a very clear pattern behind these venues. So, for example, you see autonomous vehicles driving much more commonly in the San Francisco Bay Area, where it is sunny most times of the year, or in LA, where you don't have any natural features like big mountains or slopes blocking some of the view. But these are some of the typical places where you would want to have a prototype autonomous vehicle be displayed or be deployed. Again, here I'm showing two different examples of autonomous systems. One is the Waymo autonomous vehicle, which is steering through a particular traffic intersection on its own, and the other is a platoon where there are two autonomous drones that are surveying these areas. So, for example, there are two drones, one in green and one in purple, and they automatically decided among themselves that this is the plan to survey these areas. And then you can see that the red regions are not to be messed with. So I always, the both the blue and green, try to stay out of the red region as much as possible, and then I will survey some of these regions that are specified here. So you can see that there's a clear division of labor, and we want to have this in a completely autonomous way. So these autonomous vehicles are actually beta tested in many scenarios. So I think Waymo now has more than 300 million miles under its belt. Just to put it in context, can you guess how many miles do people in the United States drive annually? So again, I'm quoting the United States numbers because this is somewhat easy to infer. The actual answer is literally astronomical. The actual distance traveled, the cumulative distance traveled by cars in the United States, is half a light year. Now, sure, 300 million miles is a big number, but it is nowhere close to half a light year. This is literally astronomical number, right? Now, is it so? Well, there is a huge gap. Does this gap automatically translate to necessarily bad thing? I don't know. So, if the half a light year distance, if half a light year um, drives are all on highways with nice weather, then probably it's not too much of a difference, even if you drive 300 million miles or 400 million miles, to give some sort of a confidence or guarantee. But the major difference between these two, as in the number of miles that are covered in beta testing versus what is in reality, the biggest difference is because of the coverage in different scenarios, right? So there are, in United States is geographically very diverse, population wise very diverse. So you would, the traffic scenarios that you would encounter among by traveling this half a light year distance is very diverse for different instances, right? So one way to think of how to guarantee these is by doing data augmentation. Again, this is true for every autonomous vehicle company. Most autonomous or every autonomous vehicle company has a photorealistic simulator in which they test their autonomous systems, and we need to have some additional ways to perform data augmentation over these over the scenarios that we have already seen. Now, there are two camps in how to do data augmentation. One of these camps is deep learning based, and another is programmatic simulation driven technique. So, in deep learning, what you do is, well, you capture how much ever fidelity of accuracy you want to capture the driving scenario in. Again, you can train a huge foundation model, which would take again a lot of money. You can feed it the multimodal data that is captured from all the cameras, from all the lidar, and then you can build these data sets, and then you can do some sort of a fine tuning and say, okay, you can maybe label some of the agents in these videos, such as this is a person, this is a car, and you can do additional labeling over these video feeds and multimodal data, and then you can then, once you have a pre-trained a large language a large model which is multimodal, then you can use some sort of a generative model to sample new scenarios. However, this is, again, there are many issues with this. Again, this works, right? As in, we know that if you go through proceedings of CVPR or ACCV, ICCV every year, you'll find many techniques building on this and trying to make the process of feeding foundation models a lot of data more efficient, sampling them much more efficient, using new generative models for sampling these scenarios. The other side, again, thinking of transporting back to something like 80s or 90s, where computational resources weren't too cheap, even like early 2000s. One way that would have been a common way that you would do this is to say that, well, we now have pretty good graphics engines. We can use these graphics engines and build a photorealistic simulated environment. So, for example, running Unreal Engine 5 over a good GPU is much less expensive than running language model on a GPU, which requires a lot more computational resources. So I can create assets in a specialized graphics programming environment, and then I will pay a programmer to code up a wide range of scenarios. You can either do this manually, or you can use some automated techniques. Here, I don't mean to say that the automated techniques are machine learning driven. You can use some classical techniques like fuzz testing, or maybe some sort of genetic algorithms to say, oh, I have two scenarios. How can I combine these two scenarios to generate another scenario, either using fuzzing? So these techniques are even now fairly popular. And if you go through software testing conferences like ISTA or ICSI or ASE, you will find several works that actually go this way, which is, I have a simulation environment in which I can test different scenarios. I have a programming environment in which I can represent these scenarios, and I can use a classical automated technique to generate these scenarios. Right. So these are two camps in which we can develop these data augmentation. Again, there has been a lot of work in both of these. There are, again, I have some references here, uh, a few interesting um, the you can think of three of the I've given three representative works here. One of them uses some sort of a scene graph, which looks at graph representation of what are the agents in a particular scenario, and then tries to transport it to tries to actually use the scene graph to generate new scene graph, and generate a representative sample of what you've seen earlier. The other uses Gaussian splatter and nerve-based techniques to actually not just simulate the view of the camera, but also simulate some sort of a multimodal data, right? So these are some of the often common techniques used, right? One of the challenges with these deep learning-based techniques is that, yes, you can generate these using by taking in large amounts of data, and you can do scenario editing. But one of the major challenges is that you cannot do fine-grained editing. Like, say, again, uh, the special scenarios needs to be represented in a disproportionate manner for actually giving some sort of a reliability numbers. So, for example, we really want to have a good representation of near safety misses, right, in the data set to test autonomous vehicles. However, for doing this near safety misses, you need much more fine grained control over the scenario editing when you're augmenting these scenarios, right? And currently, these techniques do not do such a fine grained editing, right? On the other hand, there are programming languages. Again, you can go back to developing assets and deploying assets in Unreal Engine or in graphics programming environment. But then people have come up with new higher level of abstractions. So one of them is this programming language called Scenic, where you can represent objects as physical objects in the world as first class objects in programming environment. So here, for example, what we do is, here is an example where I'm showing that I have so the programming environment helps you to quote unquote run a program in a graphical visualization scenario. So this is an example of a scenario that is displayed in Unreal Engine. So this is in GTA rendering engine, where you can give scenarios with descriptions. So you can say that I have I want to think of say three vehicles. Say there is a ego car and two other vehicles, and now what I want to do is that I want to have a distribution among these scenarios where my ego car is on a particular lane with some deviation from the center lane, and you can think of the deviation being sampled from a distribution. Here the wiggle room says that I have my orientation is not exactly along the road, but it is from -10 to 10 degrees, and these are not to these are observed somewhat in practice. So you have to specify what is the distribution that you want to sample with, and you can add some additional constraints. So for example, here I have an ego car, which is a special car where you're fixing the perspective, and here I'm adding two new cars to this particular ego car, where there are some special characteristic which says that the new car is visible to the ego car. Again, you cannot see the third car because I've cropped the image, but I have a special constraint that these two cars are now visible to the ego car, and both of these cars are sampled with some distribution that I've already specified. So this is one way where you can explicitly program distributions or program scenarios. Either you can use them explicitly, that is, you can say, oh, place this vehicle in this part of the road from this much deviation from the central lane, which is facing this way. Or you can give some sort of a distribution where you can say this vehicle is going with this velocity using this distribution, it is facing this direction with this distribution, and there are some standard distribution. You can add and subtract these distributions as well to generate much more fancier distributions. And eventually what Scenic allows you to do is to sample from these distributions specifically. So whatever constraints that you have, say I want three cars to be visible from my ego car, then it does make sure that these three cars are actually visible by, and some of these constructs are implicitly programmed within the Scenic language. So this is one way to to do this. Both of these have obvious positives and negatives. The deep learning based just works, right? You don't need anything fancy. You don't need any. You don't need the infrastructure to build a photorealistic engine. Of course, you can use one off the shelf, but again, you don't need to train your workforce to work on the specific programming language for that specific environment. You don't need anything more than just having new and interesting techniques as to how to sample these and how to feed this data to a foundation model. But as we said, the negatives are that you cannot get too full of fine-grained editability. The other thing is that, well, sure, I've given, say, 10,000 scenarios. Is there any guarantee that these 10,000 scenarios are represented in some explainable way in the scenarios that I want to generate? Well, not really, right? You are now relying on some internal representation which is again biased to some sort of initial conditions of whatever your gradient descent, to get these get some sort of a uniform sampling of all these distributions. um, the one sort of a side of this is that high dimensional data, although the we all believe that all these high dimensional data lives in a low dimensional manifold, um, actually processing this high dimensional data, which is actually processing videos and searching over these videos and modifying these videos, is computationally much more expensive than compared to just modifying text, right? On the other hand, if you use a programmatic language like Scenic to define these scenarios, there is one problem, which is that someone has to sit, or some agent has to sit, and then program these specific scenarios, that okay, this is the scenario, this is how much I want the car to be away from the center point, and this is the orientation, and someone need to specify all of this, right? So this explicit specification of distribution is actually much more tricky. It still requires someone to learn how to do, or how to specify these distributions, and again, there is a very precise semantics. Although the learning new languages, especially in the age of these language models, isn't too much of a problem, because you can use some of the auto correction or even semantic extensions of these using LLMs nowadays. But the advantage that you get is that you can actually do much better fine-grained control of scenarios. It is much more efficient, and you can get a precise semantics for whatever scenarios that you've generated. So now you can actually talk about, oh, if I have a 10,000 programs that are depicting these scenarios, I can I can do some sort of static analysis over these programs, or dynamic analysis of these programs, and show that the new scenarios are actually represented faithfully from the existing data set. So, combining these two, what we want to pursue is some sort of a neurosymbolic data augmentation. What does it mean? It means that we can hopefully generalize to many more diverse scenarios. We get good grounding, which is again the fact that when we generate a scenario, it is actually corresponds to a real scenario, not like cars flying over people and all sorts of hallucinations that you see in the video models. Um, we want to have some fine grained control. We want the scenarios to be explainable, and we also want it to be very cheap, right? So because of these two reasons, what we did is we explored this neuro-symbolic technique for doing this data augmentation. Okay, so again, the yeah so I will go to, again, back to this slide, which actually highlights the importance of not just using both the real world data, capturing it using some symbolic constraints, and also you transporting the same scenarios into a simulation engine where you know that the scenarios in the real world are captured faithfully. So what I will do is, uh, um, after motivating, I will briefly talk about some of the related work, and I will briefly go through what is the technique that we have used to transport from road to code a given scenario. Then we have some exciting new developments in terms of why I don't want to see this more as a technique, but also as a platform for actually for actually capturing scenarios in a virtual environment faithfully. And I will show some applications of this road to code, and I want to then go ahead and give some of the future work. So okay, this is the idea of transporting a real scenario into a virtual scenario. It has been around for a while, and one of this paper, which was published in ICRA, actually had this idea long before. So they want to take a dash cam video and sort of extrapolate it and have a representation of that. Again, this can be used. You can think of this having many interesting applications, either say in the case of insurance claims. Or so what they did was they took some dash cam videos, and ported them into a simulator. Again, this was fully deep learning based. So you take a crash scenario, you run it through a neural network, and then you can have have a simulation, have it presented in a simulation environment. Although this is somewhat restricted to what environments you can do this in. This is not as general as having a programmatic representation of all the scenarios. The second word that I want to highlight is Scenic NL, which was published 2 years ago in Conference on Language Modeling. So there, what they did was, again, in general, there are these long-winded DMV reports about various accidents. So they say that a car was driving on this lane, and then suddenly another car turned into this lane, and then it gives clear descriptions of the type and make and model of the vehicles, what was the speed, what were the limits, such as the speed limits, or the specific topology of the traffic that the vehicle is going through, and that is given in natural language description. So what they did is they had a bunch of scenic programs that they have already written in the database, and they tried to match natural language descriptions to the corresponding scenic program. So what they invented is they created prompting strategies and essentially fine-tuned a language model to generate these purely from natural language descriptions. Um, Again, this seems very, very similar to what we are doing. Again, another sort of work in this whole avenue is this neurosymbolic graphics, where people wanted to like take a photo or take a picture of a real world object, and you would automatically get some sort of a CAD description of that specific object. So if you take you and you can think of this being built in a piece by piece manner, which is heavily compositional. However, if you take something like a nerve, where you transport an object into into a virtual scenario, you can give some maybe object rendering or contours of the objects, but not necessarily the step by step composition of these objects. So again, this is again very interesting work in neurosymbolic models for computer graphics. So okay, these three are somewhat closely related to what we are doing, but ours is essentially some sort of extension of these into multimodal scenarios. So let me give this setup here. So suppose that you have a sequence of dash cam videos, that is, you have these RGB frames, and now what I want to do is I want to generate a scenic program and the environment. And you can think of the environment as the corresponding topology of the scenario, or how many lanes are in the scenario, what is in the surrounding, what is the sunlight like, what is the weather like, and all of these. And from these frames, I want to construct a programmatic description of how all the agents are behaving, which is the actions of these agents, and how the environment is, right? And I assume that I have some space of environment and some a restricted set of actions, right? And again, what is the measure of correctness? If I take this program and run it through a particular simulation environment or photorealistic environment, then the resulting video that is a result of running this scenic program should be very, very similar to the original video that I've taken. Again, there is the video is, although in a photorealistic environment, the original video is in a real environment. I can give some measure of closeness, like how the objects are being tracked, or some signal to noise ratio, or some of these metrics. And I want the simulated video to be as close to the real world video as possible. Okay, so again, if this was before the age of language models, what I would do is I would collect a bunch of programs and videos. Again, I can use this. I can do this either by training taking a lot of graduate students or putting this on a mechanical turk, and I'll say that, okay, this is the video, can you write a corresponding scenic program and build this database of program and video data sets, and then train a particular neural network where the input is a video and the output is a program. This doesn't work because it requires a large data set. The neural network may not converge, and it requires a diverse set of scenarios. So, in the age of these foundation models like ChatGPT, Gemini, and Code Llama, and all that, um, we can leverage some of these foundation models for fine tuning or improving the performance of some of these techniques. So, here is one way to think of this, right? So, we can think of giving the program and video pairs that you can that can, so if I have a database of scenic programs, I can run these programs and generate a bunch of videos, and then I can use just the regular fine tuning, just GPT fine tuning, and convert individual frames into scenic programs and combine the scenic program in and perform some sort of static analysis, or to make the scenic program more efficient. So we tried this, but this did not work because the scenic programs that you have to generate should have some specific structure, and there is a very specific correlation, as in humans can actually track these objects moving in these frames, and the at least in our initial fine tuning process, GPT couldn't correlate the moving objects in the scene to the specific artifacts in the scenic program. Again, this could change if we have a large enough set of scenic programs and a large enough set of videos that show the executions of the scenic programs. This could actually change, right? So, for example, if everyone watching this video decides to write, okay, I'll write 10 scenic programs and feed it to a language model, maybe with thousands of these scenarios, then this might actually work. But when we started doing this, we still couldn't get it to satisfactory results. So what we did was we did a few things, which is that instead of directly feeding the videos to some sort of a pre-trained model, what we did is we used some explicit object trackers, and we used these object trackers to specifically track these, and use the pre-trained model to where we fed the both the videos and the object tracking data to the pre-trained model, and asked us to generate natural language descriptions of the scenarios. So this natural language description is what you can think of as some sort of a intermediate representation for conversion from a high dimensional video object to a low dimensional scenic program. And from this natural language descriptions, we tried one shot learning, but it didn't work. But chain of thought prompting worked really well. So we added chain of thought prompts to for this natural language description. And once we added the chain of thought prompts, we could actually use fine-tune Code Llama to actually generate scenic programs that were actually executable, and we could actually do it much better than just by fine-tuning with just the video and the program. Again, so again, I don't want everyone to be worried that I'm flashing too much information here, but this is what the intermediate representations would look like. So with the explicit object tracking and feeding the videos to pre-trained models, we generated a huge amount of text, and this text, when fed through chain of thought prompting, actually managed to give us some scenic programs that we need not change too much to actually execute. So this was actually one of our first successes, where we showed that with chain of thought prompting and with these natural language descriptions, you can actually generate scenic programs and actually run them. Well, does this work? You be the judge, right? So here are some examples from Waymo open dataset where we generated these, where we took the videos and used object tracking over these videos and gave chain of thought prompts, and we generated a simulated scenario. And you can see that again the environmental aspects are somewhat editable, but we try to keep the environmental aspects as much as possible by adding some explicit representation within the chain of thought prompting. It can say, oh, it is broad daylight, or it can say it's it is nighttime, and some of these are actually translated to some parameters that you can tune within Scenic. So here are some examples of these frames from Waymo. Again, there are it works reasonably well in a few scenarios, but you see that let's take the third one, right? So here there are many more cars in the scenario, but some of these cars seem to be missing from the virtual scenario. Why is that? Well, again, this could be because the object detection network did not work properly, or if the object detection is static, although there are some cars parked on the side of the street, the object detection network gave that, okay, this is an object that you might want to track, but then the language model might have discarded this, and then so we still have some issues that we need to fix in terms of transporting objects where we have many more cars. So an egregious example is this, where there were like many objects that are parked, and there are other cars that are in the opposite lane. But in this particular case, either the object tracker did not work properly, for some reason this scenario did not get translated very well. Okay, so overall some scenes we did have a lot of success. So for example, this is from the new scenes environment. Again, the position of the cars are slightly off. Even in some of these scenarios, again, some of the vehicles are missing, but at least it's a first step in actually getting from a photo or from a video and transporting it to a simulation environment. Okay. um, One of the advantages of this is that we can actually make it the do some obvious augmentations, like maybe nighttime scenarios or daytime scenarios, and change the weather. That's much more easy to do in a simulation environment. What I want to do now is to not present this purely as a technique where we go from videos to text, but more to think of this as a way to change the fundamental processing pipeline itself. So till now, what I did was, okay, we have these photorealistic, we have these video scenarios, and autonomous vehicle companies are collecting these data sets in large quantities, and we want to convert them into scenic programs. What I want to do is to think of creating a data set where we are creating a virtual library of these scenarios, and using whatever techniques that we have at our disposal to actually build a real pair of video and its translation into virtual scenarios. So this got us started into data set, or again, look out for this in the near future. What we want to do, what we want to go towards next, is to have a data set where on one side you have these photorealistic, or you have these videos that are collected by these new scenes, or Waymo, or pick autonomous driving company of that is your favorite. You can take these scenarios, and you have the corresponding scenic programs at your disposal, right? Again, if you look at the new scene scenarios, not all of them are from the US. There are roughly 500 of them from the US. What we want to do is to give a scenic program for all of these, and in addition to that, again, these programs we want to derive automatically, and I'll briefly sketch how we do that. It is not as fragile as, oh, we'll feed something to object detection, and we just hope that the foundation model reads the text prompt carefully, and then the chain of thought works properly. Instead, we build in much more structure in the generation process, and instead now have a much high faithful representation of the video scenarios to the virtual scenarios. And now, in addition to that, we'll also have a bunch of golden scenic programs that are thoroughly validated. So these are validated either by saying, okay, by doing some sort of a human evaluation, or you can do some video evaluation as well. There are ways in which you can automate this process as well. But essentially, in addition to translating these 500 video scenarios from the real world to the virtual world, we also give a few bunch of golden scenic programs which you can use as some sort of a ideal benchmark, right? The pipeline for this part is slightly more complicated. So we need much more symbolic aspects in this. That is, we take into account, or we try to count, how many lanes are there. So this is where we explicitly used a lot of supplemental information that is from the new scenes dataset. So the new scenes dataset actually doesn't just give us the videos, but it also gives us how many lanes are there, what are all the objects that are tracked, and all that. So we can use some of this information. We can use the GPS information to actually extract or create explicit representations of the behaviors that are much more easy for a human to understand, and then use machine learning in individual stages in this pipeline. So first is we do some sort of data curation, where we want to make sure that the objects are properly represented. Again, because the simulator has only the towns in the US, this is a shortcoming of the simulator. We want to preserve only the scenarios that are in the US. And we use some explicit techniques for extracting the behavior of the scenario, such as whether it is turning or whether there are lane changes. And then once we extract this behavior, we can explicitly count how many agents are there in the environment, and then use essentially some of the traditional language composition technique to convert a particular video into a scenic code. So again, what is the point of doing this? The point of doing this is that when you think of when you shift your frame from thinking of this as one technique where I transport one video into a particular virtual environment, having this data set enables much more powerful analysis, which are actually much more important. So one of the obvious things is you can do data augmentation, which is one of the goals of doing this whole transportation from real environment to virtual environment. But it enables a lot more of applications which are much more useful, not just in the developer sense, but also in gaining in assuring that these agents or these autonomous vehicles are actually working properly with respect to whatever people's choices are. So, for example, you can say that I have uh, 100. So Waymo has driven 100 million miles, right? Say I want to take 100 million scenarios, or 100 scenarios from 100 million miles, and want to say that, okay, was there any point of time where a Waymo was stuck in a particular traffic jam, where there were two human drivers and both of the human drivers were waiting for the Waymo to yield to the right of way, right? Or was there any deadline created by Waymo where there was some sort of a miscommunication, right? Again, 100 million miles is a lot of data. Searching over a video sequences of that long is extremely difficult. However, searching over 100 million mile or 100 million lines of code is much more easier than searching over 100 million miles of actually video data, right? So search is one of the applications. Then the other thing that we explored is we wanted to check if you can enhance some sort of scenario understanding using this explicit program representation. So you can say that, oh, can you tell how many cars are there that are coming into the adjacent lanes of ego lanes, or is there any left turn that is happening in this scenarios, or how many lane changes happen in this scenario. So all of these talk about understanding of a particular scenario, and all of these can be enabled by having explicit representations and not just implicit representations of the scenarios. So again, I've talked about data augmentation already, so I won't bother with you that much. Search is actually much more important in, say, generating new test cases or evaluating. Suppose you're in charge of making sure that you want to grant Waymo new licenses or give permission to Waymo to operate in your neighborhood, right? What is the question that you even ask Waymo, right? Okay, are there some set of standards that you want to impose? That is, oh, can Waymo function properly in all-way stops? So in that case, you can give probably permission for it to operate in residential places, right? Here is another thing that happened very recently, right? Waymo, there's actually a court case that is going on where, especially when there are school buses around, Waymo doesn't behave according to the observed traffic rules, right? Now, can you actually search in these 100 million miles of scenarios, and can you evaluate which scenarios are up to the standard and which scenarios aren't, right? And you can think of all these. And again, the simplest way that we tried is, suppose you give me n scenarios and you give me a particular search criterion, and now I want to make sure that um, what is the best scenario that matches the search criterion. And again, we these are some preliminary results. What we have shown is that video processing is way more expensive than text processing. So what we did was, we took a bunch of video scenarios, converted them into scenic programs, and when we asked these query based searches, like give me a particular scenario where one of the non-ego vehicles is taking a right turn, or non-ego vehicles is taking a left turn, or where two vehicles came close to each other. In some of these query-based searches, video-based took a lot more tokens and is much less, and it has much less F1 score when compared to scenic-based scenarios. And we did something with similarity search as well. So I can you give me a scenario that, say, I have encountered a new scenario on when I was driving, how would have seen it behaved in this particular scenario? So you can think of giving an input, a particular video or a textual representation of a video, and now you can do some sort of a similarity search, right? Again, in that, the scenic based is only slightly better, but it takes much less time and much less number of tokens, right? Similar with question and answer queries. Again, text processing is way more easier than video processing. And again, if you have much more complicated questions that talk about agents turning right or turning left, having a programmatic representation of these scenarios takes way less time and is much more efficient and way more accurate than just hoping that the features are obvious in the video and these are accurately represented. So again, okay. So what are some of the limitations? Again, I'm not saying that this is done. Um, as I've shown examples before, if there is a scenario with too many vehicles, sometimes the object detection might fail, or sometimes these things are not actually translated properly. So so there are still some shortcomings where scenarios with too many cars may not be translated. The other example is that Scenic only talks about the behaviors of the agents and some constraints, and you can generate distributions of scenarios where you can contain some you can change the behaviors of these agents. However, it doesn't fully talk about how to encode the physical environment. There are only a few places where you can do this, But if there was a place where you can actually generate the environment, like, okay, there is a new virtual scenario where I have 3 lanes on the left and 2 lanes on the right, and then the intersection is such that it is a very weird geometry. Again, we have all been through these scenarios, right, where the turn, it is not exactly 90 degrees, but it is more than 90, and you always go into the other lanes while turning. Again, we have all been through such scenarios. So generating those environments much more easily is still not too easy to do purely using Scenic. So we need some additional infrastructure for this. Yeah, so again, there are some incorrect translations, that is, the behaviors are not translated properly. Another challenge is that, suppose that I give you a data set where I have a video, and I say this is the corresponding Scenic program for this video. Doing the validation is still somewhat hard, as in you're still relying on some machine learning model to say, yes, the number of cars in the actual scenario is same as the number of cars in the Scenic program, and the behaviors are similar. But how to actually validate it, right? The validation, again, the only way to validate is that you actually need to take the measurements in reality and compare them with the measurements in the in the simulation environment, which is slightly hard, but at least you can get a broad level validation. The only advantage is that when you have these programmatic representations, you need not worry too much about the validity, because our goal is to make sure that the autonomous vehicle behaves properly in a wide range of scenarios. So as long as the scenario is behaviorally equivalent, you don't need the hard validation. But it's a very interesting, but it is actually somewhat of a challenge. What I want to do is, in the future work, there are many interesting ways where we can think about it. One of them is that right now most of the scenarios, we haven't explicitly tracked pedestrians and cyclists, but again, this is something that we want to add. Again, in behavior augmentation, there are, again, the sky is the limit, right? You can think of supercharging neural network based behavioral augmentation techniques using Scenic, right? So you have a scenario and you want to edit the scenario, you can use Scenic program as the intermediate representation for to supercharge your neural network based behavior augmentation. You can think of prompt based generation, where Scenic all the prompts are now converted into Scenic, and you actually run the Scenic program through some sort of a neural network and show it, right? Again, search queries, search and question and answering, you can, especially with the road to code data set, you can use many interesting techniques. Right now we just presented using some sort of prompt engineering based techniques, but I can think of pre-training a code model with all the data, and then using this search in an interesting way, right? The another interesting way is how to translate a scenario from one topology to another. Say, for example, I'm in a very busy intersection. So there is an adage which says that if you can drive in New York and Boston, you can pretty much drive anywhere in the United States, right? Why is that? Maybe the scenarios that you have seen are way more complex. So how do you translate this complexity from one physical topology to another, right? So again, this is the future work is actually much. There's a lot more to be done using this road to code framework. And I want to stop here and take any more questions. So with that, I will end my presentation, and thank you for your attention.
Thank you so much, Sridhar. So, yeah, very, when we curate from the really rapidly increasing number of neurosymbolic papers, one of the things we're looking for is things that can either are or could have a really large impact practically. So, really encourage this kind of work. So, thanks, Sridhar. So let's take some questions. I have some myself, but let's see.
Yes, actually, we do not have much from the audience. So maybe everything was very clear. There was just a couple of comments like how great it was and excellent lecture. So, Alex, maybe we can start with our questions. I actually have a couple questions.
Yeah, go ahead, Olga.
Maybe like not very much about your research, but I'm just curious, Sridhar, you're focusing on this area. Do you personally trust existing self-driving cars? Would you considering owning one yourself? Yeah, you live in North Carolina, right? So probably it's like good weather all year round. Maybe it's not a huge megapolis something. So do you think like current state of self-driving cars is in a good enough shape even for these conditions, or we're still not there yet?
Yeah, that's a very interesting question. The my answer is I still don't know. I think I would definitely trust a self-driving car in, say, in the San Francisco Bay Area or Vegas for sure, because I think last year the number of uh, drives or number of rides in Waymo were more than Lyft in the San Francisco Bay Area. So again, there is a tipping point, and they have a lot of infrastructure built around in making sure that at least in these geographic regions they can drive somewhat safe. But there is actually a court case that is happening as of now, where a Waymo actually, again, no human driver would do this, in a sense that there is a school bus that is parked, and whenever there is school bus, even when you are 16, it is drilled into you that whenever you are near school bus, be very very careful, because there are like a large number of restrictions. What Waymo did was absolutely inexcusable. That even when the so when the school buses stop, there is a stop sign that turns out from the school bus, and then you are not supposed to travel even on the opposite side. What Waymo did was come behind the school bus, go around it, and actually harm a student who was walking, right? So now this is actually something that happened, and this is so is it there yet? I don't know. I wouldn't trust anywhere within a school bus, right? Maybe within other cars, sure. In On highways, it is actually slightly tricky, because Google is way more conservative when it comes to deploying on highways. But yeah, so the uh, yeah, I think I would definitely trust it in 5 years. From my prior was that I wouldn't have trusted them in 2019. Now I trust in San Francisco and all these places. In 5 more years, I will have much more trust in them. That's what I would say.
Okay, thank you very much. And we actually got a question from the audience. There are trajectory prediction network for end-to-end autonomous driving. How can we ensure that the predicted waypoint's trajectory is safe for driving? Any suggestions?
So yeah, that's an excellent question. So I think the the typical perspective coming from machine learning world is that accuracy is the king, right? That is, I want to train a machine learning network where, if my machine learning system is accurate, then it is good, right? But any engineer would say that, sure, I can have a very accurate neural network, but I need to account for cases where it is not accurate, right? So from the perspective of designing an autonomous vehicle, having an accurate trajectory prediction network is useful, but the controller which actually uses this prediction network is even more important, right? So the I would say that the way these would be useful is that you just don't have one prediction or one trajectory prediction, but instead have like a top k predictions, and then the planning and the planning technique which actually takes into account these trajectory predictions should actually account for all of these. And again, I can see very easily why this has to be a neurosymbolic way, because again, the the different um, trajectories that are possible can have different modalities. So you can suppose that again, there are all sorts of instances where a vehicle that was taking a particular turn wouldn't just turn on its indicator, right? What are you going to do? The trajectory prediction network will say that, oh, with high probability it is just going straight, so you can safely make your u-turn. But then if it makes a turn, you are creating, at least you're potentially being going to an unsafe scenario. So it's not sufficient to just have accuracy be the full end goal. For, again, I come from the how to design systems in a reliable way, and in ensuring that the the extreme focus on improving accuracy is probably not the way forward. We need more techniques, or more systems engineering techniques, which actually takes into account how to classify the predicted trajectories, and indeed design better trajectory planning techniques from that use these trajectory prediction networks.
Thank you very much. We received another question. Can you recognize or represent scenarios that involve multiple steps, such as parallel parking? And there is a comment that there are some entertaining videos about two Wemos trying to do that.
Yeah, I think so. Okay, that is actually, so I would say that we are not there yet, and the reason for that is, first of all, we don't have yet capacity to do long videos. I think right now the videos that we can generate are up to 30 seconds, and these parallel parkings can take up to a minute or so. But I would say that it is possible. I think at least the way that we are doing it, it is principled, where we are again, we are not just relying on the neural network or the foundation model to just one shot the scenic program. We are constructing these explicit symbolic representations from the neural network, and I don't see a fundamental challenge in translating this to translating these parallel parking scenarios to actual behaviors. So I think it is possible, but we are just not there yet.
Thank you. We received another question. Sridhar, sampling has been a complex issue in many machine learning initiatives. You believe we are getting in a new stage using LLMs for generating data as opposed to sample from huge populations?
Yeah, so this is again a very interesting question, right? There are two ways of looking at sampling. One is statistical sampling, and here I credit one of my computational geometry friends, Don Shi. He was at NC State, where he said that there is statistical sampling and then there is geometric sampling, right? Statistical sampling can just ignore a bad case, which is statistically not relevant. Geometric sampling, you cannot ignore the bad case to actually have a geometric representation of all the behaviors. LLMs are extremely good at statistical sampling, right? That is why a lot of ChatGPT essays look very similar. I'm an educator. Ask me how many emails that I get, which sound awfully similar. Again, it's generating from a statistically plausible data, so I can actually figure that out, right? In the case of, so there is an exciting opportunity to actually bias these LLMs to actually go more towards geometric sampling. I don't know how to do that yet. I don't have enough statistics or LLM internal understanding, but I think we are at an interesting stage where you can at least prompt some of these LLMs to push towards generating geometrically represented samples. However, I don't think LLMs are going to give you purely from statistical outcomes. We need some sort of a symbolic way to actually feed the LLM that, look, these behaviors are statistically very similar. Give me something that is geometrically different from these. And I think this is another place where I think neurosymbolic sampling techniques can actually play a big part.
Mhm. Thank you very much. These are all questions at the moment. Alex, you mentioned you have some questions.
Yeah. So I think this thing you were just mentioning about geometric sampling. Yeah, I also worked a little bit in computational geometries. Yeah, and I think it's, as you said, I can't think of a way you could get to that kind of sampling without a symbolic representation, or at least something that I mean, no matter how you want to phrase it, something that explicitly represents the underlying structure, semantics of what you're wanting to sample from. Then that's no matter how long
Yeah.
you make the sentence, it's somehow symbolic. So to me, at least, I can't think of any other way. Uh, but then my next question is, and I have a few questions. So one is um, the extent to which the detail level of that semantics. Of course, I mean, it's difficult enough with the current representation that you have, I assume. Of course, ideally, it would be very detailed. Then you can, as you're mentioning, you'd like to go to smaller objects and like bicycles and so on. And
Yeah.
but let me just maybe if you could review the current level of what you're modeling in this scenic language. Like,
Yeah.
do you have, for example, I know maybe you said it and I missed it, or maybe you could talk about the temporal modeling aspects, or the aspects of it as in terms of like actions, or a situation. Like, I'm thinking like situation calculus, event calculus, this kind of thing. Ordering and multiple steps, as it was brought up, with parallel parking as an example. What's the detail level at the moment?
Yeah, so right now the scenic allows us to represent objects and motions of these objects. So, for example, it is not a graphics engine yet where you can say, oh, these are going in this way and they collide and then they move away, right? Graphics engines are very good at even simulating the physics. In scenic in scenic, you need to give how these are behaving at the action level. So in fact, what we are doing is in some sense very simple object tracking, and to some extent it's somewhat preliminary in a sense that we are not even tracking some of the predicates that are important. So for example, say there are the uh, the two scenarios, or rather, yeah, so the level of detail that scenic allows us to do is we can we can declare some properties of objects, that is where they are, what's their orientation is, and how are they behaving, that is what is the behavior of this object in the next frame for the next few frames. However, we do not have a full scale physics simulation where, oh, this is how, there is no intelligent agent driving this car, and now you simulate that within scenic. I think it's possible to do it in scenic where you can deploy another learning agent within this car and you can run these, but right now we are still not there yet. uh, we are also not tracking some of the predicate information, such as say there is a vehicle that is taking a unprotected left, which is the biggest cause of accidents in the United States. If I'm taking an unprotected left, my when did I start and with which speed I went through can feel more dangerous because of the velocity of the other vehicle, right? So, in that sense, we are still not adequately capturing how dangerous it felt. We may be, we for a extremely confident driver, they can calculate and they can say, okay, this is a scenario that I can do very easily. But someone who is a less experienced driver might be, or more cautious driver might be apprehensive of taking that, right? So we are not tracking some of these high level predicates of the scenarios, but only at the behavioral level. That's where we are at as of now.
And so things like a sort of situation model or activity recognition type thing, that's not quite there yet.
Yeah. So nothing about, say, some sort of intent recognition or someone signals something. We are not explicitly tracking any of them. Yeah.
So just more broadly, I mean, we do a little bit of work in robotics. It's very typical. You train your robot in simulation. What I think we're seeing is, maybe there is some of that, but we're seeing training of self-driving cars with real data, which you wouldn't, if you were a university, say, you wouldn't try to do that. It would be way too expensive. But if you can do it, I guess that's the experiment. Throw a huge amount of money at it and get that data. But even if you could do that, that's, I think, your line of thinking. Well, okay, but you can't test out of distribution scenarios, and that's actually the problem. That's like where you have, it's the stuff you haven't seen before. That's the, suddenly there's a bird on your windshield or something, and so it doesn't seem like there's any. I can't think of any other way except creating those scenarios in simulation. So to create enough of them and so on. And not to mention, if you want to sort of suddenly make your car work in, I don't know, on the streets of some city, in another country where suddenly there's an elephant crossing the road, or so actually seems more cost effective if you can you can actually just do a lot of that training and simulation. But how far would you? I think that's the direction you're going in, right? So, but how far would you say we are from that?
So I would say that actually the from whatever I read and understood, um, the disengagement numbers that are reported by some of these autonomous vehicle companies, they, at least by Waymo, actually takes into account how it behaved in their photorealistic internal simulator. So it's not just like a place where, oh, okay, the driver engaged in the driver took control of the from the autonomous vehicle, so that counts as disengagement. No, it says that they do extensive simulation in the photorealistic environment of the same scenario, and then try to say, was it, did the did the backup driver react preemptively or more cautiously than what is required. And they are already accounting for this, and pretty much every autonomous vehicle company does train their systems at least partially in some simulation environment. The only trouble with purely relying on simulations is that the data is, as in, if you train something in a simulation environment and you deploy it in the real world, there is the sim to real uh, uh, gap, which people are still working on. But in the long term, I don't see any other way of, again, uh, any other way of simulating at least much more diverse scenario. So for example, uh, the when you mentioned that, uh, when you said, oh, if you're running in a if you're running in a different country, right, the geography might be very different, and you can have a specific sunlight happen in a specific way, and that can actually interfere with the driving patterns, right? Now, how do you actually simulate that? You can get some guarantee on the way your vehicle behaves by doing it explicitly in simulator, right? Right now, there is no obvious tool as to how to even convert a real world scenario into the simulation engine. So we are at least working towards it. I believe that simulation is at least a first step in doing some of these reliability analysis, or even some sort of a cost benefit analysis, right? You can imagine the following, right? I take a before actually deploying a car that is worth $100,000 in very busy streets, where the liable is that if you make an infraction, then you have to pay up something like $5 million, right? What you can try is, okay, I have my mapping cars anyway. I'll take a bunch of dash cam data, and I will convert all of them into simulation scenarios. And now I will run my autonomous vehicle in these simulation scenarios, which will at least give me some sort of a cost benefit analysis of, okay, is this even worth doing this, or do I need to actually where do I even start, right? So when you said there is some implicit distribution of scenarios, right now the implicit distribution is somewhere captured in the amorphous space of pixels and intensity values in these pixels, right? By having these programmatic representation, you at least have a symbolic object which gives you actually a distribution. So I think that, so we just believe that these are actually a distribution. You can actually say, oh, is this a distribution or not, by actually looking at the scenarios, and at least explicit representation of scenarios. That is what I would say.
Alex, I have a couple more questions.
Please, yeah.
A stupid question for me. Actually, two questions, different but related ones. The stupid one is, did anyone ever consider using video games data for training? Probably it's not the best driving in the world. And then second related question is, are examples of bad driving ever used in training? Like whatever this behavior was, you, Waymo, should never do something like this.
So okay, your question about video games is not at all stupid. I actually wanted to take all the video game data, and they're like, again, they have these agents, right? But to my utter shock, what I realized was, if you actually go into and dig into some of these video games literature, the behaviors of all the vehicles in something like a Need for Speed or whatever these car racing games, all of those are deterministically programmed. The other agents, like, oh, there is some other car that is driving beside you, even that, there isn't too much of AI being used there, because they know the track of all of these. There is not, again, Need for Speed isn't, it's an exciting game. It is not a game where you are going from your home to a grocery store or anything, right? So they can actually flaunt all the traffic rules, and again, it would be a very boring game if you are going to get some milk and come back, right? No one gives you any points for that. So these data, so I was hoping that the surrounding vehicles data could be useful, but all of them are pre-programmed, and that's why you see, again, next time you play any Need for Speed game, you'll realize that those vehicles, whenever anything hits them, they just stop. Why? Because it's a deterministic engine that's already programmed into them. So again, I went into that rabbit hole. It's a very interesting question, but the the game the we cannot pay people enough to play a game where you go safely from home to office and office to home. That game won't sell. Even that, you won't get even a cent out of playing that game, right? So yeah, so that is one. What was your other question?
Other question was about examples of bad driving.
Yeah. So
From
yeah,
computer games or from real life, let's say someone has example like recording of a crash or something. Uh, is this data ever used?
yeah. So I think I cannot speak to. So what I do know is the following. At least from whatever I have written in the San Francisco Bay Area, they have figured out the pedestrians very well. Again, I would say this: if you actually look at Waymo negotiating with the pedestrians, at least in the San Francisco region, it can actually do a better job than me, because I'm coming from the southeast, and there is some driving etiquette which is somewhat polite and giving away. That doesn't fly in San Francisco. So these quote unquote bad behaviors are already in the data set, and they are actually using this in the training purpose. I'm not sure whether they are too worried about specifically bad driving. Like, I mean, the if you search for bad driving and look for videos online, there won't be a dearth of it, right? Reddit is full of these bad driving videos, but fortunately, these are way sparser than what we imagine. Right? Fatality, the rate of fatality for human driving is 1 in 100 million, right? So again, I'm pretty sure if you're slightly conservative and if you're driving in carefully calculated neighborhoods, staying away from extremely troubled areas where there's like extremely high traffic or high speed traffic, you won't get that much of a fatality anywhere, right? So just by sampling the places where you drive carefully, just by sampling your routes carefully, you can cut down on some of the exposure to terrible behaviors much more easily. I'm pretty sure that is a calculation that is done already internally in any of these companies that wants to be serious about future aspirations of autonomous driving. I think it's not a surprise that most of these are in either San Francisco or Arizona or Vegas, where the sun shines all the time, the roads are very wide, or at least they can actually predict the behavior much better. In terms of, yeah, I how to deal with some of these bad driving, that will be that will be a question that will be asked in 10 to 15 years, where say 5% of the cars are autonomous, right? But right now I think they can defer that answering that question. So there is yet not too much money in answering the question, so they'll probably ask that question when it becomes economically important.
Thank you very
All
much.
right.
Yeah, Alex, we're almost at time. Yeah.
Yeah, just one last question to conclude. So, part of our purpose is to help inspire students and researchers on new problems. So, what would you say if you were to paint the holy grail, of full success for your research agenda? What are some things we need to pursue to get there that you would encourage students and researchers to work on?
So yeah, that's an excellent question. So in fact, I myself have been studying more neurosymbolic systems a bit more closely. In fact, this semester I'm teaching a advanced graduate course on neurosymbolic systems, where we are reading papers all the way from computer vision to programming to robotics to language models to generative models. So from my reading, uh, um, autonomous driving is probably the best case for neurosymbolic stuff, because the symbols are there, right? It's a car, or it's a person, or it's a vehicle. You don't see that much noise. In Again, there is a lot of noise, but you're not distinguishing different species of bugs, or different species of different configurations of trees and humans, or occlusions, or all these, right? There is a very structured environments on which autonomous vehicles drive. at least in the case of autonomous vehicles. I would say that neurosymbolic techniques are a success if we can at least handle one problem, and that one problem is some sort of data augmentation or testing or search, right? Uh, I think there is a lot of so okay. People want to develop trust in autonomous vehicles. What's the way to develop trust? You can't show them 100 million miles of videos and so oh, we drove it properly. Say someone wants to program a scenario and find out how does an autonomous vehicle behave in that scenario. Can neurosymbolic techniques be useful in synthesizing a test scenario that I have in my brain very easily, right? How can I synthesize these scenarios in a much more interesting fashion? These are all some of the so I would say that neurosymbolic techniques, at least in this case, would be a success if we can solve at least one problem, like maybe data augmentation or search or question answering, one of these machine learning tasks, much better than or much more efficiently with the same accuracy than some of the traditional machine learning techniques. And I think it's not too much of a tall ask because you need to process the video once. You're anyway doing it by feeding it to your large foundation model. But now I'm going to give you a benefit of having a symbolic representation, which you can do many more things over, right? So I think at least I want to pick one problem and show that this really outshines any of the methods out there, even that explicitly use purely neural network based representations.
All right, my cat is letting me know that we're at time. All right, well, thank you so much, Sridhar. Thanks,
Yeah.
everyone.
Thank you so
And,
much. Thank you for having me.
Yeah, if you have time, jump on Discord if there are any questions.
Alex, sorry, maybe we can quickly announce next week. So next week we are going to have Paolo Torrizelli presenting his work about whether transformers can find logical rules. So please join us next week.
All right, thanks, Olga. Thanks, everyone. Take care.